Okay. Couple things. The my apologies for not have the last computer assignment was has taken me an extra long time to grade because some of you nailed it and some of you didn't. So, and that's trying to figure out what kind of went wrong and takes a while. And so I did post the next one, which is going to be the most challenging one so far. And my concern is, and I gave a little more time, so it's not going to be due till next Wednesday instead of the shorter one. But I feel that there's some things that need to be some confusion about how to translate the event graphs into the code, because what I was seeing was some things that weren't doing that. In other words, the event graph says one thing and the code says another. So it's like they should be more or less consistent. So so basically, I mean, if you ran it and you got, and some of you got slightly different numbers for this, it turns out that you can do it correctly and get different numbers than I did, just because and when we cover how random variates work, it'll be kind of a little clearer why that might be so. But so if you ran it and you got numbers that were kind of close to what was in the handout, then you're good. I mean, it is the thing with these models is it's almost impossible to get numbers that just don't go wacky if there's something egregiously wrong with the model. So and it's also easy to get numbers that are slightly different and still correct. So that's just there is a certain degree of randomness in this, even though, as we talked about last time, strictly speaking, there's no such thing as true randomness. There's pseudo randomness. Bless you. And just peeking ahead a little bit, just to kind of maybe understand why that is. You may have noticed that when you're, since the beginning, as you were building the model and you ran it, you kept getting the same numbers. So it's like even going back to the arrival process, when you when you ran it, you'd get an arrival at a certain time, and then you'd do something else, and then you'd get an arrival at exactly the same time again. So why was that? Where's the randomness? By default, the random number generators in SimKit use a fixed seed rather than a random seed. That can be overridden. I mean, if you want to seed it with the time and other stuff, it's absolutely possible to do that. We can talk about that when we start covering that. But imagine trying to debug a model, and every time you run it, you get a different result. So I mean, that's crazy making. So right. So there's that. So in other words, and I'll try to get the final ones released. But if your numbers were okay, then you should be okay. There were some where ran it and was sort of getting an error, and then in those cases, when I kind of looked at what was happening, there was almost always a situation where the code did not match the event graph. So, for example, in the customer entity, it required two numbers, a service time and a renege time. And so there were some cases where it was only given one of those, and sometimes in some cases it wasn't given any of those. So just kind of watch out for that, because that didn't match what the UML diagram was. And in other cases, so for example, like if the event graph has no arguments, then don't put an argument on it. Unless the event graph is wrong, but in this case, the event graph was right. So anyway, so the model. So today we're going to delve a little bit more into these array states, what this index property change is about for that, and the next computer model I'm going to have you do is really kind of a pumped up version of the transfer line model, and it's kind of the most involved one that we have. The event graph itself is fair. Again, I think it's fairly straightforward, but if just based on seeing some of the struggles with the Renegade model, my concern is that would get, for those of you that kind of didn't quite land on that, that my concern is that will sort of carry over this, and that's not what I want. So I want to make sure that that the whatever disconnect there was for the last assignment is sort of fixed, as it were, so. Okay, so having said that, I'm going to charge ahead. I don't know, I probably told you this story, but in my graduate school, I foolishly took some advanced math classes over in the math department, and this one in particular, the instructor was this Russian, he'd come over from Russia, and in Russia they have a much different mindset with all of this. So but I mean, imagine you're sort of, I don't know how you are with math classes, but it's like, I mean, imagine the worst math class that you've ever had, where it's like all this sort of gobbledygook and just these weird symbols and everything. So that's what it was like. So he would have these proofs that would fill the whole blackboard. He'd start at one end of the blackboard, he'd get to the very, and then it was like, well, what the heck is going on? So he gets to the end, fills like 3 blackboards worth of these symbols that we're just trying to copy down as best we can, and without any real understanding. He gets to the end and he looks at the board and he looks at his notes and he looks at the board. And he says, "Oh, I see that there's a mistake in this proof. Does anybody see the mistake?" He says, "Well, if nobody sees the mistake, we'll just go on." So, anyway, so I don't want to do that. It's the bottom line here. Okay, so array states, and where we're headed is this sort of this full-blown transfer line model, and so array states, and this is, I've mentioned this before, but it bears repeating. When we have a state variable that's an array, we will typically only one element of that array is going to change at a time. I mean, that's kind of by the nature of these events. As we'll see in the transfer line model, like one of the array states is going to be a container of queues. Well, take a simpler one, the number of available machines at a particular station. Okay, but if we have n stations, then we're going to have n of these things, and we're going to do it in an array. And so if we have let's say, a begin processing or start service at a particular station, that's only going to change the number of available servers at that station, nowhere else. And just as I hope you're kind of seeing, the nature of the event model is that it kind of changes a portion of the state space at any one time, but just sort of one at a time. Okay. So what information do we need? Well, what we need is we need to know, well, what is the name of the state? What the new and optionally the old value is. But most importantly, we need to know the index of the state. And now, as we've seen, how does anybody outside of the simulation component know that a state variable has changed? And the answer is that they don't unless they're told. And the way that they're told is, well, in the SimKit one, it's by firing a property change. And that's because that utilizes the property change stuff in Java. For the Python ones, it's notify state change because that's actually a more descriptive one. But what those do is they fire a property change that it only impacts anybody who's listening. And the two important things for listening is that when you're debugging the model, you can make sure that the correct state transitions are occurring by listening for that with that simple property dumper or simple state change dumper. And that's how you know. And that's how we're able to avoid putting print statements in the components, so we don't have to go and delete them later. The other one, and that's sort of the key one, are the statistics. So the idea is that we listen for these state changes and then update our statistics. And we've seen the simple stats tally, the simple stats time varying, and then the collection size one for those. And for index changes, we have each of those with the prefix multiple in the Java case, and then the prefix indexed, because that's more descriptive. As we dealt with why the difference? Well, because as I'm a little challenged when it comes to names, and so my first attempt at a name usually kind of screws it up, and so with the other version, I thought anyway, that's not important. Okay, so let's all right, I want to give an example. So let's say, like here's another arrival process like thing. So, we've seen some kind of onesies and twosies types of things, but what if we want to produce n arrival process like events, but each with their own intra-arrival times? And so now we want to do all of this in one component. And so this is just an event graph. So we have the number of processes, and then an array of inter-arrival times, which are going to be in the implementation, typically can be random variates. And then now our state is also an array, and that's going to be the number of arrivals in the ith arrival process. And so what does that look like for an event graph? Well, what we need to do is we need to put n of these arrival events on the event list. And so we do that using our, hopefully you recognize this pattern as the for loop, the event graph for loop. And then every time, for every one that we have, we're going to schedule an arrival event, and we're going to pass it the index of that. Why? So that the correct state, that is the number of arrivals, is scheduled correctly. And the delays, the two delays, are also correct. And then once we have the arrival, it's going to schedule the next arrival, but it needs to pass the index of that. And if we're kind of interested in listening to that, we would need to fire an index property change for that. So So I said I'm going to implement that. So let's see let's see what that looks like. Okay, so let's create a new Java class. I'll call it indexed arrival process. And our superclass is going to be sim entity base. Sorry. Well, why does it do that? Let's exit the show. So what was happening was it was not showing us. Got it now? Okay. Okay, called the indexed arrival process. And we're gonna, the superclass is sim entity base. So we're, we can't really use, well, we'll do it from scratch here. So, but let's, okay, parameters and state. So how do we go about doing that? We start with the parameters. And so an array of random variates. And let's see, we need to fix imports for that. And and actually, once we pass this, we can kind of, in cases like this, we can optionally skip the n, because that's going to be given by the size of this. So, but, and this is how I like to do things. Okay, and I write the constructor, and that's because of this peculiarity of NetBeans, where it likes to, okay, we're going to refactor, we're going to encapsulate the fields, we're going to select them all, and then we're going to put them in the last method. And since it's an array, the next thing to do is to clone, make sure we're cloning our arrays here for encapsulation. And then just for completeness, I also like to have a getter with an index that returns the index. And likewise with this, for just for completeness. And this is a Java beans thing. And then when we're doing this, and you might notice that we're not being super careful about the indices, but we're going to leave it at that. And now we need to put our master constructor in. And here just the okay, so there now again, where did all this come from? All this came directly from just the parameters. That's all I've done so far. And in fact, what at this point, what I will do, what I always like to do, is then, as soon as possible, start running things. So I'm going to test the indexed arrival process. Okay, so what do I need? I need an array of random variates. And we can just sort of create them on the fly here. We always get our random variates from the random variate factory. And let's, just for, let's use a Weibull and a uniform. What else do we have? We have exponential. Okay, so all I'm trying to do is just make sure that my my class has the right parameters. That's the very first thing that you should do. Okay, so all I've done is I've put the parameters in, and all I'm looking for is to see whether or not they got in. And in this case, I'm sure they're going to get in. Okay, so I was printing the. And if it doesn't come up what you expected, there are a couple of things that could go wrong. But here, okay, so the 3 that I wanted got put in. So, I mean, what could go wrong? Well, what could go wrong is I could forget to do this. And if I do that, then all of a sudden, what I get is a null pointer exception. Okay, so it says, well, blah, 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 because, okay, it says, this arrival time generator is null. Okay, why is it null? So it's like it shouldn't be null. So how can I sort of test that? Well, I can debug, put a breakpoint in here. Okay, I made it there. That's okay. So let's step into this, and then I say, oops, I forgot to do that. All right, so now I want to do this, the state variables. Okay, now here's where, oops, the state variable needs to be protected. And now here's where things can get a little bit dicey. If you do the encapsulate fields in NetBeans, first of all, we don't want a setter. You need to change the field's visibility to protected. Otherwise, it'll change it back to private. Okay, so, and again, we want to clone that, and then we also have our getter with an index. Okay, so let's see what's, all right, so now, so here's the thing. Now, when we have an array state variable, we're going to get null pointer exceptions if we're not careful. So we want to make sure, at least on the Java side, we want to make sure that this has always been instantiated. And so we will typically instantiate these in the constructor. However, the problem here is that we don't know we don't know how many to do in the zero argument constructor, but we do know in the master constructor. So the idea is that that's one way to do it. The other is to instantiate it in the reset method. And so let's actually, that's what I'm going to do instead. Okay, the reset method is where we initialize things. But for arrays, by the reset method, we know how many of these are. And so we can initialize it there. But our run method, and there's a similar thing, you know, like for the Python people, I'll do this in Python, but kind of offline. All right, so what we need to do on this, all we have are array state variables. And we want to schedule our init with 0, a high priority, and with a 0. Now, if we want to be extra careful, let's kind of look at our event graph here. Okay, so the event graph says no condition. So we're going to assume that we've been given the right number of things. So we'll just kind of do that. Okay, so for the initial one is what we want to do is set the index of this to 0. Now, they're going to be 0 to begin with, but we need to do that not because of what we're doing here, but because of when we run it again. So and here's where the convention is that when the new value, you should almost always get from the getter. Okay, so now if our index, remember it was less than 1, n minus 1, but oops. Okay, so this is, we're simply implementing this piece right here. And then the next thing to do is we want to test that. And we can do that. This is where our simple property dumper comes in. And then we want to run it in verbose mode. And so for that, in the Python, you would simply set verbose. So here, well, the schedule reset is going to reset everybody, and schedule start simulation is good. Okay, so what am I looking for? I'm looking for, in this case, you're going to be 3 init events that where I see the property change, state change is going to be the correct. Yes. And let's see. Okay, so we're still, always print this out. And so, okay, so here's our run event. Here's our init with 0 scheduled. So the number of arrivals 0 is 1, number of arrivals 1 is 0, and number of arrivals 2. So couple things that could, what this means is that the number of arrivals array was correctly instantiated. And the other thing is that it was correctly initialized by this. So now we're almost there. We just need to schedule this. So in addition to that, we'll now schedule an arrival. The delay is the index, and we're going to pass the index to that. And actually, so by adding that, I still, notice that I'm as soon as I can run it, I'm running all kinds of things here. So what I'm looking for are these arrival events. So notice that the init, because it's priority. Well, actually not for this, but I'm looking for the arrival events building up. So 0, 2, and 1. Now, why is that? Well, because the delay times were generated at different values. Okay, so check. So, and then finally, and I don't do anything else until that's working. That's the. Okay, so okay, so I have an arrival with my index. I do the old value, new value thing, which is only on the Java side. Number arrivals of the index is just for everyone, and then we fire an index property change for, index. Number of arrivals. And here I got the old value and the new value with the index. And then finally, I want to schedule the next arrival event with the inter-arrival time generator of the index, passing the index. Okay, so now now if I run this, it's going to, I'll do it just because it's going to go out of, why? Because I'm not stopping it. Before it was running out of events. So now I just need to, okay, so let's stop at time 20. And we see that, okay, the arrivals are happening. And we would check and make sure that all of the state transitions were correct in that. Okay, so that's how you take. Let's share it again here. Let's see if we can get this to work. Okay, so that's how you take this and turn it into. And the thing is that you do that for everything. All right, so now let's look at this transfer line model. So now we've done, I think, at least one. But now we want some additional metrics that were not available when we were doing it the other way. So we want, okay, we'll want an explicit delay in the queue at each workstation. We want, and then in addition to that, for each part, we want the total time that they spent in the queue on average, as well as the total time that they've spent in the whole system. And we also want metrics at each workstation. So like, what is the average delay in the queue at this workstation? What is the average time in the system at this workstation? What is the average number in the queue at this workstation? And then just because the instructor has this fetish with Little's formula, it turns out Little's formula, let's see if it applies at each workstation. The claim is, regardless of what your system, you define your system, Little's formula will hold either exactly or approximately. And so let's test that. So our transfer lines, they say with n work centers, and now the terminology, we're going to use work center or station and machines for our servers. And so you have parts coming in with an arrival process. They're going to be processed, in this case, there are three machines at the first, 4 at the second, 2 at the third, and each part has to go through each one, waiting in the queue if there are no machines available. So now, as you saw, as we've seen in the previous assignment, in order to, for example, get the total delay in the queue, what we're going to do is we're going to have I'll call it a part. It's going to be an entity, and it's going to keep track of that. In other words, it's going to have a my part objects are going to have the total delay in the queue, and I have a getter so I can get it. But then now how do I increment that? Now there are a couple ways I could kind of do it by hand. But if you remember, the delay in the queue we did using that elapsed time thing with the internal timestamp. And so for this, I want to encapsulate that by just calling increment it. And then internally, it's going to update it based on the elapsed time. Okay, so parameters, again, these are our usual suspects. We have the number of workstations. Again, that just as we did it, just as what I just did, you could either have that as an explicit parameter or leave it off, because the length of these arrays are going to be you can use for n. I forget whether I put it in or not. It's like you have to kind of pick your poison. If you put it into the implementation, then there's always kind of the danger it'll get off a little bit. You know, in other words, if I say that there are 5 workstations, but I only give it 3, then things can get a little weird. But for the sake of the event graph, we don't have to worry about that, because we don't get these array index out of bounds exceptions when we're doing everything in pencil and paper. So now our state variables, okay, the first 2 are similar to what we've done on the entity server. So we have the number of available machines as an array that's initially equal to the number of machines at each station. And then now we have a FIFO container of parts in the queue at that station, which is initially, actually, this is incorrect. It should be empty. each one should be empty. That's about right. And then, okay, now we wanted the delay in the queue and the time at the station for each one. We've done that previously in the entity server. So we're just going to do it at each station now in an array-like thing. And then two scalar arrays, two scalar variables, I mean, the total delay in the queue, which is one that we wanted, and the total time in the system. So now, in terms of events, well, let me go right to the event graph on this. So, our scalar state variables, we're going to initialize in the run event. Our array state variables, we're going to initialize using a for loop. Now, as the for the SimKit ones, kind of Java pulled a thing a few versions ago where they made it illegal to have an array of collections, which made it kind of weird. So what can you do? Well, in the implementation, that is for this queue, in the implementation, and hopefully I remember to put that in the write-up, you just have an array list of sorted sets. So that's how we do that. But okay, so now here's the thing. Now our arrival event, so that's the arrival of a part to a workstation. Okay, now notice that even saying it like that, there are two pieces of information, which part and which workstation. And so we're going to have two arguments. So the part, we're going to stamp the time as we always have, we stamp the time so we can at each workstation, so we can calculate the delay in the queue and the time at that station. So we stamp it and then we add it, we add that arriving part to the ith element of our queue array. So we need both of those pieces of information. Now, we may schedule I'll call it start processing, just because we're kind of machine oriented here. And the condition is that there's an available machine at that station. So we need that I there. But we don't need the part. We don't, and just in general, for these types of events, we get the part by popping it off the queue. We don't pass it in. And okay, so this is all just like the entity server. And here's where we call that increment method on our part. Remember, we had defined they say increment total delay in queue, but I mean I'm going to abbreviate that to just increment here. Okay, now when we finish processing, again, just how do we completely describe it? We finish processing on a part at a particular workstation. So end processing needs to have both of those pieces of information. And so it may schedule the next part in its queue. And if it's not the last station, it advances to the next one. So this is, again, this is the same as the previous one. But now we're adding, in order to get those last two bits of information, we need a new event. And I'm going to call it part complete. So how do we know it's complete? Well, if we just finished at the n-1st station, which is the last one. Why n-1? Because the silly off by 1 zero-based indexing stuff that you've heard me complain about for the past 5 months. But that's just what it is. So if we're finished, then we say, the part is now complete. And so we can get the total delay in the queue, because we've incremented it in each workstation. And well, what about the total time in the system? Well, that is the age of the entity. Remember, every entity has a creation time and an age. And so the time between when it was created, when it showed up at the first workstation, and so its age is how long it's been in the system at that point. And then the total delay is something we've kept incrementing here. And then so these would just fire an ordinary property change because they're scalar variables. Everything else is going to fire an index property change. And so now our part arrival process is going to be very similar. Now here, notice that the transfer line is going to handle the processing times now, not the part. We could have done that. I mean, I have a model that does that, but I wanted to keep it simple, as simple as possible. Okay, but we still need both of those pieces of information for the arrival. We're going to the 0th workstation, but the part doesn't need any extra data. It doesn't need a service time or a renege time or anything like that. No, it's just accumulating the information, but it still needs to schedule that first arrival. And I encourage you, like I noticed this, some of you were doing the kind of redoing all this stuff, but I encourage you to kind of to do it this way. You don't have to. I mean, if you want to redo all this sort of stuff here. But again, now this isn't that indexed arrival process stuff I was doing earlier. This is just a regular old friend, the arrival process, and it's just sort of scheduling these. So okay, now unlike this class, I actually have 3 minutes. So I'll tell you what I'm going to do. I'm going to I'll just start the part thing for you just to kind of show it. Okay, so what does that look? What I'm looking for here, and I don't need to override the constructor because it's but what I do need is a you need one of these, and I need the getter for that. So let's encapsulate that. I don't want a setter. This is the last method. Okay, so now how the total delay, I want to okay, so that's in other words, what this is assuming that whoever is directing the traffic on this has stamped my time at the arrival. Am I sharing this?
I can see it.
Okay. So assuming that at the arrival the part has been stamped and that this has been called at the start service event, then every time it does that, it will update it by the elapsed time. And the reason to do it, or the advantage of doing it this way, is that now I don't need to do the calculation elsewhere. I just need to make sure I do this. And then at the end, like if I've gone through like 3, 5, 10, however many stations I've gone through, every time I go through a station, this will get incremented. so that when I get to the end, I'll have this going on. Okay, so I will commit that, and then for those of you in Python, I'll kind of redo what I did before and commit it later this afternoon. Okay. Any questions, concerns? Probably some concerns, but no questions. Okay, so yeah, this okay, and then the lab at 1, that's going to be just on Zoom, not in person.